Okie dokie. So once we know how to use a right triangle to find some trig values, we sort of did this without necessarily knowing anything about the angles. So what comes next is we can actually look at two special triangles, so two sort of particular triangles that have some particular side lengths that'll give us some particular trig values that we'll end up using a lot. We're going to end up using a lot. So our first special triangle is a 45, 45, 90. This, as you can probably imagine, is a triangle. It's isosceles. I'll do my best to sort of draw it. That's a pretty decent looking. So right triangle where the two inner angles are both 45 degrees. 45, 45, 90. Who would have guessed? And so in theory, right, depending on how sort of big or small you sort of draw or make this triangle, you could have all sorts of different side lengths on here, but the ratios will be consistent. And the one that gives us, in some sense, the nicest possible versions is if we just set both of these legs equal to 1. Now, if both of those angles are 45, then the side lengths across from them are going to also have the same length. I'll spare us from the details of it, but if you do some Pythagorean theorem, you would imagine a squared plus b squared is 1 squared plus 1 squared is 2. So then c squared is 2, which means our c value here would be square root of 2. So based on this, what we can do is we can sort of use this to find different trig values for a 45-degree angle. Trig values for theta equals 45 degrees. That would also, in radians, if you did a quick conversion in radians, that would be pi over 4. So we can just do this based on this sketch. If we can kind of quickly make this sketch, or if we have it in our notes somewhere as a reference, we can sort of then use it, leverage that, and find all sorts of trig values. I won't do all 6 necessarily, but let's do a handful of them. Well, I don't know. We'll see how long it takes. Maybe I'll do all 6. Who's to say? But let's start at the beginning. Let's start with the sine. So sine of 45 degrees. Sine should be the opposite over the hypotenuse. And so one of the things that's happening here is, depending on your perspective angle, 45 or 45, they're both the same. So either 1 or 1 is the opposite. That must mean that it doesn't particularly matter, right? So let's say, just for the sake of argument, we're using the 45 down here in the bottom right-hand corner. So then 1 is the opposite, and then root 2 is our hypotenuse. We're going to have to rationalize that. So we'll do that move times root 2 over root 2, and so our final version here is going to look like root 2 over 2. So that would be our sine value. If we flipped it and did our cosecant, what I would do is I would flip this version, right, and I would flip root 2 over 1 would just be a single root 2, and that would be that. These are fast, so I guess we'll just go ahead. Cosine of 45 degrees. So now we're talking about the adjacent over the hypotenuse. The adjacent and the opposite, again, they have the same length. So what's going to happen here, right, is we're going to get 1 over root 2 again. We kind of know already what's going to happen. That should be root 2 over 2. And then I guess what that means is if we flip it and do a secant, what we're going to get is root 2 over 1, which is just going to be a root 2 again, right? Just to save space, I'll do our tangent values over here. Tangent at 45, so that's going to be the opposite over the adjacent. So again, these are both 1, right? 1 over 1. So that means the whole thing here is 1, and then pretty quickly, if I do cotangent and flip it, I'm just going to get 1 over 1 again, which you would imagine is still just 1. So 45, 45, 90, right, it's really an isosceles right triangle. So the other two angles are both 45s, and so we get this sort of nice ratio between all the lengths. Gets us these values. The next special triangle, so we're only doing 2. Try to keep that in frame for a minute at least, is the 30, 60, 90. You can imagine, based on the names, this is going to be used for either 30-degree angles or 60-degree angles. So this one has a little bit more information. So we use for theta equals 30 degrees. If we do a conversion, that would be pi over 6 in radians, or theta equals 60 degrees, which would be pi over 3. I'm kind of only doing these examples in degrees, I suppose, just to sort of save time a little bit. But in theory, you could redraw this, either of these triangles, and label them with radians, and of course do the exact same work that we're doing and come up with the same answers. 30, 60, 90, I'll do a little bit of a breakdown. So what we would do to get a 30, 60, 90 is we would actually start with an equilateral triangle. So that's the angles and the sides are all equal. So that would be 60, 60, 60. And what we're going to do is use side length 2. So 2, 2, 2. To make this into a right triangle, what we're going to do is cut a line straight down the middle and break this into 2 individual triangles. And so then what happens here is if I sort of remove 1/2 of the triangle, I'm going to get something that looks kind of like this. So I've got a 60 down here. I've got a half of a 60, right, because I'm cutting this angle in half up top, and I have this nice right angle on the bottom. And so what do I know about the side lengths? Well, I know that the one over here is a full length, just like we started with, so that's 2. The bottom of this, the whole idea is that we cut it in half, so then this length is going to be 1. And again, I'll save us the calculation, but if you do some Pythagorean theorem, so 1 squared plus, this would be b squared equals 2 squared is 4. 4 minus 1 is 3, and so this is going to be root 3 over on the left. So what this allows us to do is find sine, cosine, tangent, any of these 6 trig values for 30 or 60, depending on how we want to sort of do this as a perspective. So I'm not going to do all 12 values here. It's a little bit silly and kind of redundant. So let's do a handful for 30, and then we'll sort of switch our perspective and do a handful for 60. So let's start with the classic sine of 30 degrees. So 30 degrees is up here in the top corner. Our opposite for 30 would be down here, would be 1 on the bottom. Opposite over hypotenuse, so that's 1 is across from the 30, and the hypotenuse is 2. So that's pretty lucky, so 1/2. Cosecant, I just can't help myself from doing reciprocals as well because they're so easy. Flip it, 2 over 1, so the cosecant is going to be 2. If we do cosine, 30 degrees, so that's the adjacent over the hypotenuse. That's going to use the root 3, right? So the adjacent is root 3, hypotenuse is 2. If I do secant and I flipped it, so 2 over the root of 3, that one we'll have to rationalize, right, because it's got the root on the bottom. So that's going to look like 2 times root 3 over 3. Ending up with our sort of rationalized ones in green, I guess. Not on purpose. What the heck, we got time. I guess maybe we'll just end up doing everything before all is said and done. I'll do my tangents over here again. So tangent 30 degrees, so that's opposite over adjacent. So my opposite is 1, my adjacent is root 3. Rationalize it. Root 3 over root 3, so this is root 3 over 3. And then our cotangent, if I flip it, will be strategic. Let's not flip the final version, let's flip the version in red. Just flip it based on the original 2 values. And we'll just get our root on top without too much trouble. If I flip my perspective and I want to look at this from the 60-degree perspective, so now I'm sort of looking down at the bottom right is my angle. Root 3 is the opposite and 1 is the adjacent. 2, of course, remains the hypotenuse. I'll change my colors. And let's do, so sine 60 degrees. So opposite over hypotenuse. So now 60 is here. So root 3 is the opposite. 2 is the hypotenuse. That means if I flip it, cosecant 60, going to have to do some rationalizing. But you can kind of see pretty quickly that one of the things that happens here is we end up repeating a lot of the same fractions. It's just that different functions end up with those final values. So what was the sort of secant at 30 is now the cosecant at 60, because the sine and the cosine at 30 and 60 are going to sync up. This makes sense from just a geometry kind of perspective, right? Because if we're taking the same triangle, right, a 30, 60, 90 is sort of, so 30 degrees from one perspective, 60 from the other, but the side lengths are all the same. So we would expect to sort of end up with the same types of fractions. They just get sort of shifted around. One of the things that's going to happen for us with all of our trig values is we're going to see a lot of repetition. We're going to see a lot of the same stuff happening over and over and over, but from different perspectives. Cosine 60 then is going to be 1 over 2, right? The adjacent is down here versus the 2. Flip it, we get 2 over 1 for secant. Last pair, tangent 60 degrees. So that's my opposite over my adjacent. So that's going to be, so root 3 over 1 is just root 3. And so then you can expect cotangent, once this gets flipped around, 1 over the root. When I rationalize it, I'll get this root 3 over 3. So tangent and cotangent are kind of here and here. Their roles are getting reversed if we do it from the other angle's perspective. So gosh, we kind of did them all. So that was all 6 trig functions. At all 3 of these are going to be sort of our kind of main go-to angles. So 45 and then 30 and 60. Partially this is of course just because they sort of take something like a 90-degree angle, which is sort of one of our quadrants, and it breaks it up really nicely. Just to think about just the smallest little picture tagged on here at the end, right? Why do we care about these in particular? And so part of it, right, is if I have kind of 90 degrees here, 0 degrees here, if I do, right, 45 straight out in the middle, and then 30 and 60, what I'm doing is I'm taking 90 and breaking it up into 3 chunks. So 45 breaks it into 2 chunks, 30 and 60 split the difference. And so if you can kind of visualize, right, 30, 30, 30, this would be 30, this would be 60, and then out to 90. Versus the blue, where we're kind of going 45 and then 45. So the patterns here and the values that we get, these are all in our first quadrant, right, from 0 to 90. The patterns that we get and the values that we get here are going to end up repeating over and over again. We're going to get particular patterns, particular fractions. They're going to end up repeating in the other 3 quadrants, quadrants 1, 2, 3, and 4. But we're not quite there yet. They're going to end up with a couple different changes. But a lot of this all comes back to this right triangle stuff, being able to sort of draw a triangle, find the opposite, the adjacent, and the hypotenuse, and then kind of using these definitions. That's really something that's never going to go away. A lot of the trig that we do, you can sort of trace back to that kind of a picture and that kind of an explanation.